Next few slides, I'm just going to be building some equations to a set that we will use for this class. So we have our equation already for average velocity. It's change in position over time. And if time 0 equals 0, if we just start the watch and that's where it begins, we just have change in position over time here. And similarly, we can talk about acceleration as change in velocity over time here. If we rearrange the second equation and solve for this v, we can get v equals v0 plus at. Just a little bit of algebraic manipulation of those variables. This equation holds for constant acceleration. So that's one of our constant acceleration equations we'll be using as we go forward. In addition, as velocity is increasing at a constant rate, if we have constant acceleration, so it's changing by 15 meters per second every second, we know that the average velocity will be halfway between the start and ending value. If you start at 0 and end at 60 meters per second, and you're uniformly accelerating, you're uniformly changing your velocity, then your average velocity is going to be 30. So we can calculate our average velocity as the starting plus the ending, divide by 2. So if it were 0 to 60, divide by 2, the average velocity would be 30. If algebraically we combine this equation with the equation I had in the last slide, we can get to this one. X, our final position, moving, say, in our uniform straight line, equals our starting position plus v0t, our starting velocity, times the amount of time it takes from starting to ending, plus 1/2 at squared. A is our uniform acceleration, and t is the amount of time it takes between starting and ending points. All right, and if we recombine those equations again, we can get an equation in this form. And if I put all those together, I have a set of equations that I can use for constant acceleration problems. And we will use these in this chapter. We will use them again in the next chapter, and they will occasionally show up throughout the semester. So I recommend that you get comfortable and familiar with these equations. I realize they start out looking a bit like alphabet soup. It's an awful lot of variables thrown at you at once, but take your time, play with them, solve some problems, and they'll become familiar, and hopefully you'll become comfortable with them. All right, I've made note that for each of these equations, there's an assumption that the acceleration is constant. We do not have a change in acceleration. That is a key criteria for these equations to hold. And I also note that these are the equations as written in the Giancoli textbook, but they perfectly correspond to the equations as written in the OpenStax textbook following these equation numbers as well. The exact same format was used in both texts. All right, to start to get a little bit familiar with these equations, let's ask a few questions. So you're asked to solve for acceleration, and you're told it's a constant acceleration problem, and you're given a final velocity, an initial velocity, a final position, an initial position. What equation do you use? And to solve this, it's a bit of a hunt and peck. I'll look at these, and basically I want an equation that doesn't include time, because time is a variable that I wasn't given, and I don't have acceleration. So if I want to be able to solve this in one step, and sometimes we can't, but if I wanted to be able to solve this in one step, if I'm given all 4 of these variables, is there a way to solve for acceleration when I don't have time? If I look at these, this one's no good, it depends on time. This one's no good, it depends on time. But this one will work. This third equation doesn't depend on time. I can solve for acceleration if I know final and initial velocity and final and initial position. So this equation will work. So I've rewritten it down here. Here's the equation. And I usually solve things algebraically. So if I were given values for these, I would first take my equation and rearrange to solve for A, and then plug in the values. Unless one of them's 0, then I might just drop out that term right away. But if I had non-zero values for these terms, then my first step would be to rearrange. And I can subtract v0 squared from both sides and divide by 2 times the change in x, and I will have the acceleration. So acceleration is final velocity squared minus initial velocity squared divided by 2 times x minus x0. All right, I do want to touch a bit on problem solving, how to go about solving physics problems. This is often a topic of anxiety. Many students in this class are very good at memorizing information, at learning the concepts really well, but when it comes to problem solving, there's a small panic. And I would say, don't panic. Try not to panic. I give yourself a set of steps that you're going to go ahead and follow that will help you. The first thing I do is I always start with grid paper. I find that I work more creatively when I am on graph paper. I feel it's easier for me to spread out in all directions on a page as opposed to trying to be linear. It's easier for me to jump around a bit. So that would be my first recommendation. Second is don't expect to get it right the first time. Don't expect that you can sit down with a physics problem and necessarily be able to solve it from start to finish correctly the first time, especially with those constant acceleration equations. Sometimes you have to solve for one variable before you can solve for another. It is an involved process, and it may not be obvious to you right when you start what the steps are. So don't panic if that's the case either. All right, and then following the guidelines given here, make sure you read the whole problem. Make sure you understand it, then read the problem again. There's nothing worse than working through a problem and realizing you solved for the wrong variable, or you didn't notice that it said constant acceleration, so you had the wrong physics applied. You thought that the acceleration was varying, something like that. So read the whole problem, make sure you understand it, read it again. Decide on the objects under study and what the time interval is. So object under study, that's usually fairly obvious, but not always. Sometimes you have one object, say, pushing against another, and you have to say, look at all the forces on one of those objects. Make sure you realize where you're making a force diagram when we get to that. So decide on the objects under study and what the time interval is. A good choice of time interval can help you significantly with your problem solving. Sometimes it's obvious, but sometimes you will choose a less obvious time interval because you have some insight into the physics at a particular point in time. And we'll see that as we do example problems. Next, if I could, I would insist, I implore you to draw a diagram. Draw a diagram of the problem. Do this for your homework problems. Do this when you're taking an exam. Drawing a diagram is one of the best ways to visualize the problem, make sure you understand what you know and what you don't know. Draw a diagram. Choose coordinate axes. Usually I choose an XY coordinate system and I make X be positive to the right and Y be positive upward. But in some cases, people choose Y to be positive downward. So, look out for that. Then go ahead and write down your known or given quantities and then the unknown quantities that you need to find. And now it takes a little bit more thought. You have to consider what physics applies here. If you're told it's constant acceleration, that's an important piece of the physics that is in play for a particular problem. And then if you can, try to plan an approach to a solution. If you don't know, you can if you know it's constant acceleration, write down those constant acceleration equations, consider those, and then see if from the knowns that you've written down and the equations that you've written down, if you can figure out an approach for solving. And so, as I say here, which equations relate the known and unknown quantities? Reconsider, are those equations valid in this situation? If you've written down constant acceleration equations, but there isn't actually a problem where the acceleration is constant, you know that your acceleration is variable, then you need to reconsider. So are the equations you're using valid in this situation? Then try to go ahead and solve algebraically for the unknown quantities and check that your result is sensible. So there are a number of ways for seeing whether a result is sensible, and one of them is the correct dimensions. If you need to solve for a speed or velocity, your dimension should be meters per second. If you get just meters, that would be a distance. If you get meters per second squared, that would be an acceleration. So make sure your result makes sense in terms of dimensions. Go ahead and work through, calculate the solution, round it to the appropriate number of significant figures, which for chapter 1, I care all about significant figures. From chapter 2 onward, report to 3 significant figures and we're good. I'm not a significant figure police in this class. I want you to focus on the physics, not on significant figures. So back again, look at the result. Is it reasonable? Does it agree with a rough estimate? If you were calculating the speed of a baseball pitch and you got the equivalent of 1,000 miles per hour, you would hopefully know that that is not a reasonable value. So make sure it seems reasonable. Does it agree with a rough estimate of what sometimes you don't know what a reasonable amount is, but as we become more familiar with the units, we do more examples, I think you'll get a better sense of what reasonable speeds are for different situations and so on. And then when we're all done, check your units again. I'm a big fan of checking units, making sure that those agree with the measurement that you're going for. One of the most common examples of motion with constant acceleration is falling objects. So near the surface of the Earth, all objects experience approximately the same acceleration due to gravity. So if you, for instance, have an apple, like supposedly Newton was inspired by an apple and his discovery of gravity, if you dropped an apple, it would have an acceleration. It would be changing its speed with time. And if we drop the apple from rest, the acceleration due to gravity is just around 10 meters per second. So every second it increases its velocity by 10 meters per second, speeding up as it falls towards Earth. If you know you have a constant acceleration problem, you can pull up our constant acceleration equations. Here they are again. So these equations hold when we have a problem where we know the acceleration is constant. So any falling object is an example of a problem for constant acceleration. Or if we get back to our object here, well, here, if we just drop it, it's speeding up as it falls, an example of constant acceleration. If we can take our object and we can throw it straight up, no horizontal component, if I can throw it straight up and have it come straight back down, that's better. Probably got out of the camera view though. Straight up and straight back down, that is also an example when it's actually in the air, experiencing gravity. That's also an example of constant acceleration. It is slowing down as it goes up, comes to a velocity of 0, and then speeds up as it falls back down. But it's constant acceleration the entire time. It's always changing its speed by 9.8. We'll find gravity is 9.8 meters per second every second. So in the absence of air resistance, all objects fall with the same acceleration, although this can be hard to tell in an environment where there's air resistance. So we ignore air resistance in this class unless told otherwise. So barring air resistance, so here's a flat sheet of paper that's slowly floating to the ground versus some tennis ball or rock. If we wad up the ball so there's no significant air resistance, if we drop them both from the same height at the same instant, they will both fall at the exact same rate of gravity, 9.8 meters per second every second, towards the ground. So again, the acceleration due to gravity at the Earth's surface is approximately, and if we're not told to worry about otherwise, the acceleration due to gravity is 9.8 meters per second squared, which means we're changing our velocity by 9.8 meters per second every second. And if we go to an example from the Leaning Tower of Pisa, and we drop an object here from the top of the tower, and there's our acceleration due to gravity pointing down. And this is an example where positive y was made to be downward so that as it fell, we could plot things going up on this axis to the right for plotting it. We start out at, if we make this y equals 0 and we're dropping things, after 1 second, we are moving, we have a velocity of 9.8 meters per second, but we've gone a distance of 4.9 meters. And you may say, how is that? Well, think through that constant acceleration. We start at a velocity of 0, and after 1 second, we have a velocity of 9.8. So half that time we were going slower than 4.9 meters per second, half of 9.8, and half that time we're going faster than 4.9 meters per second. So on average, our average velocity there for that entire 1 second is 4.9 meters. So we've gone 4.9 meters after 1 second. We're now moving at a speed of 9.8 meters per second. After 2 seconds, if we work through the math, our position will now be, we will have dropped 19.6 meters. After 3 seconds, we will have dropped 44.1 meters, and so on until we hit the ground. So constant acceleration, 9.8 meters per second change every second. And because we're accelerating, our velocity is constantly changing. So we've gone a little bit of distance in the first second, more distance in the second, and even more distance in that third section as our speed keeps increasing. All right, I have a few finishing slides on graphical analysis of linear motion in one dimension. I referred to these concepts near the start of this video, but just to show you, again, if we have a plot of time on the x-axis and position on the y-axis, and I can now show you really well that rise over run gives us our slope. So delta x over delta t, which is our measure of velocity, will give us a slope. Here's a graph of x position versus t time for an object moving with constant velocity. So if it's a constant velocity, the slope on a distance versus time graph will be a straight line. It's a constant slope. We're going constant velocity, we get a constant slope here, and the velocity is the slope of that curve as shown here. Now if we want one more example of, say, a velocity versus time and position versus time graphs. In the previous examples, I've talked about position first and then velocity. In this case, I've shown velocity first because I actually think it's easier to think about velocity. Here we are at a stoplight. We hit the gas. We're speeding up. We get to point A. We go to constant speed. We hit the brakes. We slow down. And then we continue again get to some lower speed. And then we continue onward. This change in velocity is shown here by position. So starting out, we were at 0 and we hit the gas. We were speeding up. So from the starting position up to A, we are increasing our velocity, and we can see that here that our slope is gradually increasing from basically 0 at here, and then our slope is, which you could take a tangent to this line at any point, which is basically a tangent is, imagine this line is a curve and a little section of the curve is a circle. Draw the radius of the circle to that point on the line and take the perpendicular to that radius. That'll give you the tangent. All right, so as we go from 0 up to A, the slope of this line is getting steeper, and that's corresponding to an increase in velocity. From A to B, our velocity is constant, so our slope should be constant. From A to B, we are a straight line, a constant slope. From B to C, we're slowing down, and our slope is dropping from B to C. And then from C to D, we are again going at a constant velocity, and that is a straight line from C to D, representing a constant velocity. One new point that I would add to that is that the displacement, if you have a velocity versus time graph, the displacement is the area beneath that curve for velocity versus time. So that can give you some useful insight. We have 5-second intervals here for the bars. So in the first 5 seconds, we're going fairly slowly. We haven't covered a lot relative to the other. When we're going faster, we haven't covered a lot of ground, and our displacement is fairly low. That pink area right here is pretty small. As we speed up, the pink area under the curve becomes greater, and so on. We've averaged things here in 5-second intervals. If we want a more accurate estimate of displacement, we can go down to, say, 1-second intervals and calculate that to figure out the displacement, or even finer still. Regardless, you can see that as the speed increases, the area under the curve at higher speeds is greater, corresponding to a greater displacement. All right, that finishes what I want to say on these topics. We added a discussion of acceleration, motion at constant acceleration, some insight, hopefully, that will help you for problem solving, a bit of discussion for falling objects and how those are a common example for constant acceleration, and a bit more discussion of graphical analysis. And just to review some of the key ideas we've covered in this video and the previous video, kinematics is a description of how objects move with respect to a defined reference frame. Our distance is the change in position of an object when measured by following the taken path. So if you had a pedometer, how many steps would the pedometer say you had gone? Displacement, in contrast, is the change in position of an object when measured from its starting position to its final position, regardless of path. So for instance, if you were at an oval track, an outside track for running on, and you went around the track once, and let's say it was a 400-meter track, your distance if you went around the track once would be 400 meters, but your displacement, if you go back to the exact same starting point, would be 0. So a really clear example of the difference between distance and displacement. All right, we also talked about speed and velocity. Speed is the distance traveled divided by the time to travel that distance, whereas velocity depends on displacement divided by the time. So if we go back to that oval track, your distance, say, would be 400 meters, and let's say you did that in 90 seconds. So 400 meters divided by 90 seconds would give you your average speed, but your average velocity would be 0 meters divided by 90 seconds because you wouldn't have any displacement. So again, a really important distinction there. So going around a track once, you'll have a certain speed, the distance around the track divided by however long it took you, but your velocity will be 0 because if you start and end at the same point, because your displacement will be 0. All right, we also talked about instantaneous velocity, where you can get a snapshot of the velocity for a very small increment in time. Average acceleration is the change in velocity divided by time, so we're being really clear the difference between distance and displacement, speed and velocity, and now with acceleration, which to have a non-zero acceleration, you have to have a change in velocity. Instantaneous acceleration is the limit of acceleration as the time interval becomes infinitesimally short. And then we introduce our equations of motion for constant acceleration, and there are 4 of those equations, and each one requires a different set of quantities. You can figure out which equations to use depending on a particular problem. And finally, we talked about falling objects, and this is also true for objects being projected. At this point, we're in one dimension, so straight up, straight down would be a 1D projection. Near the surface of the Earth, all falling objects experience a constant acceleration of 9.8 meters per second squared, meaning they change their velocity by 9.8 meters per second every second. All right, that's it for this material. I'll come back and do some examples of problem solving, and then we'll move on to kinematics in 2 dimensions. See you then.